My name is Roel, R-O-E-L, which is short for Roelof. Roelof is my full real name, but we never use that. The last name is even worse. It consists of three words. Wijnaendts van Rijnzand. It's a Dutch, all Dutch name. But I only use the first part, so that makes it easier. I grew up in the middle of Holland, in a small town, and I went to the grade school, that's the name. And I was a very bad student in the school. Well, not really very bad, but not very average, you know. So I changed to a engineering school, like a Fachhochschule. I don't know if you know this. Yeah. This in Utrecht, the biggest town in the area there. And there I was really one of the best students of the class. I graduated from this engineering college. I went to the Dutch Army, and so I decided that I would sign up to become an airplane pilot, because I was still young and crazy, you know. Then after a few months, they didn't like my attitude. I was always asking questions, you know, and that's not what you do in the army. I went then to a school for electrical systems of a Hawker Hunter airplane, and then after the army, I started looking for a job. You know?
Well, you know, this is a very different and diverse background to what happened next, right? That you got a job to the EMBL. So I'm curious, how you, with that kind of training, how did you find this opportunity, and how did you come to Heidelberg in the end?
Yeah, it won't take too much longer. After I took a job at the FOM Institute in Amsterdam. There was an atomic physics institute. They were also working already on plasma fusion, which were very optimistic at the time. And then I went to the United States, to Syracuse, and I was there the electrical engineer of the chemistry department. And the main job was the cleaning of the variable transformers, you know, because in this environment they get dirty very quickly. So I didn't have that much work, so I decided I will go to school there, because you get free credits. It's a very expensive university, but you get per semester you get 2 free credits. So I did the GRE examinations, what you have to do in the States. That was difficult, but anyway, then they accepted me, and I started to work for a master's degree in electrical engineering. And the chemistry department professor that I worked with, we got really good friends, and he let me do an experiment where measuring the motion of small particles in liquids, because they were doing plastic development. They wanted to know the molecular weight of this little particle. And if you shine a laser through that, the scattered light will have the Doppler shift of the light wavelengths on that. So then we built this autocorrelator, because it's a very slow frequency change with respect to the wavelength. And I built a whole correlator, and I was the first one to use a microcomputer, or a mini computer that was for this application. And one day I was back in Amsterdam to this institute where I was an engineer, and then I said, well, I am now a master in electrical engineering. And then they said, oh, that's interesting. And the professor was Kistemaker. I don't know if you know the name, but he was a famous Dutch professor at the time, and he was the head of that institute. So I mean, you know how it goes. You come in the room, and he has the black boy. So, oh, well, why don't you explain me what you did in Syracuse? So I did, and he was totally, they say, flabbergasted that was possible. He never thought about. I mean, lasers were still fairly new at the time. So
development, yeah.
Yeah, and they said, we're going to make you. an offer to get your PhD here. And that's what I did. And then after 4 years, I got a PhD in atomic physics, cum laude. Yeah.
Okay, so this was your education,
and then
many fields of education.
That's my problem. That's what my boss, Professor Loss, always said. You have to stick with one field, then you can become famous in that field. And I already had heard, I was looking for another job because I thought the atomic physics was very boring because there's so many theoreticians and they can calculate everything exactly, and then you have to build some apparatus to check it, you know. And I didn't think that was very exciting. And I was, of course, interested in biology. I stopped halfway here and just went to the lab here. And I rang the door. I mean, there was almost nobody working there yet. And then Leo de Meyer, he was there, and then Leo de Meyer knew about the work that I did in Syracuse. So then I said, oh, that's interesting, huh? Maybe I should apply for a job here. And Leo de Meyer thought that was a very good idea. I had made an appointment with Kendrew and de Meyer, and I got an interview. And then, of course, it was okay.
But then, what was the challenging of developing techniques to actually do the imaging of cells, right? Because this was
that was sort of a half project. The first year, I spent some time checking some properties of channel plates. I don't know. That's a quantum detector that you put in vacuum. And because I needed that in my previous job. And at the same time, I made a proposal for what the group should be doing. I got a whole new group and money, but of course, and then I wrote this proposal, and it exists on a remote-locked laser system, big argon ion laser with a dye laser, and you could make UV pulses out of this, at that nanosecond pulses. It was revolutionary at the time, so I figured you should be able to do something with that. And then one of the applications was going to be this scanning. It is an object scanning confocal microscope, and since we had UV light, good UV light, we could do very good fluorescence measurements. And with a confocal, at that time wasn't really known so well that the confocal microscope for resolution improvement was not very dramatic. But as you use fluorescence, you actually get a completely 3D resolution of the object in your cell. You focus on something, and if that fluoresces, then you see exactly where that is. So then with the scan and the computer and all that stuff, you could really make a 3D scan of a cell on a sample. And we made that very early, and wrote a paper, and of course some competition figured that they should be the original paper. But there's a lot of competition.
But then I was reading also that then you actually built a physical model of the cell also to communicate to other scientists.
Just with layers in a block of plastic. And I went to all kinds of meetings, and
what you had seen, right? Because these were the first images.
That was the first 3D image of a living cell.
Of a living cell. So I guess it's a great start. Of course, there had been already some electron microscopy of sections, of course, but this was fluorescence, and reconstructing the cell. So I mean, there's a lot of I guess instruments that you contributed to develop that weren't there, and then I guess another stage of this work has been that essentially you contributed to transform these experimental machines in essentially products and instruments.
Well, that was not really my thing. No.
It wasn't your thing. Okay.
No.
But how did?
I had a good contact with all the applied physics people in the area in Heidelberg, And they all came over and looked and said, oh, well.
Okay.
And then at that time it was very easy to get venture capital. And that was 5 professors, if I include myself, then. And the venture capital, we got about 10 million D-marks venture capital from Siemens to develop some sort of a lithography tool. And another 10 million from investors, just investors.
So yeah, and you know, building these machines for experiments, I guess, you know, this must have been your main job. But if you think about now, I mean, now, you know, there's very sophisticated microscopes and things that have been developed from the original physics that you were studying. So what are you following still the field? What are you excited about for the future?
Well, we continued, of course, the theory of confocal microscopy and all the variations. And Stefan Hell, he was in my group also as a visitor. Okay. And of course, we always had these brain sessions, and the incoherent microscopy was also part of our ideas and so. But well, that sort of took off by itself. You know, there was another experiment that I did with the same laser system. That was measuring the binding of proteins to DNA. Because if you change the pH of your solution, you can change the binding rate. And I got many visitors that were interested in that, and I could measure the change in binding by measuring the polarization of the decay curve from the fluorescence, also fluorescence. And that worked very well. So, and then of course I'm trained as a physicist, and physicists always try to make models of what you observe, you know. So then in the chemistry of the binding to DNA it's a chemical process basically. And it's a very non-linear process, so it's very difficult to do this mathematically, write a Schrödinger equation for this process. But I tried that anyway, and it looked not so bad. So I remember and I was talking about that in the EMBL. And so one day I gave a colloquium on what we did, measurements and fits the curves and so. But the biologists didn't like that too much.
There was too much physics into it?
There was too many equations on the blackboard.
Okay, well, you probably got to the limit of their understanding of this.
But I learned a lot of the biology too. Not really mixing stuff. I'm not very good at that. But I always had the technicians from it that can do that.
But I think one interesting aspect, if I may, is that you know, there's always a level in biology where you want to observe. Then experimentation means we're going to modify and things, but you know, I always tell my students that you know, one of the basic steps is observation, being able to see and describe a process without even interfering. And sometimes, you know, interference is always good, but also can introduce adaptation, artifacts, whereas you know, being able to build machines that can see is always, you know, the first step and a good step. So in terms of other machines, I mean, did you get involved in some ways also in improving on electron microscopy, and what was your experience there?
Jacques Dubrochet once asked me, because I was an atomic physicist, which I am, I guess, asked me to give me some a college of a lecture on the interaction of electrons with matter. And that was actually what we did it with ions in the institute where I did my PhD, with ions, lithium ions to lithium gas, and then the electron jumps over. You get this very interesting process, really. And so I made a course based on the things that I knew with Jacques Dubrochet. I don't know if they've learned anything, but anyway.
Well, eventually, I think something, was helping because you got the Nobel Prize.
I thought it was fun, and they came every I think I had 10 lectures or something.
Okay. Well, to finish, maybe you can tell us a little bit about, now that you have this perspective and you have been through all your careers and you can see science and in general, the future, how could the future be for science? If you have any thoughts on these and, something, maybe some message for young scientists and young generations for the future.
Well, probably with you the same. It starts always with an interest in a hobby or something. And if you are on the way to some result, stick with your subject. I would say that would be the best advice, because I never did that. And then you become sort of crazy.